Hello everyone, I welcome you all. Now I am going to explain natural convection operators in our heat transfer laboratory. All of you know about what is meant by the natural convection. Before going to the convection, what is meant by the convection? All of you know about the convection. The convection means a transfer of heat energy from surface of the object to the surrounding fluid. That is called the convection. This convection process occurs in the form of in the natural way, that is called the natural convection. That is, the convection process occurs by the density variations is called the natural convection. The aim of this experiment is to find out the heat transfer coefficient, natural heat transfer coefficient, keeping the rod in vertical position and keeping the rod in horizontal position. Definitely there is some difference is there, keeping the rod in horizontal position and keeping the rod in vertical position, because the characteristic length plays an important role here. At the time of the experiment, this one is the keeping the rod in vertical position, and this one is the characteristic length, and keeping the rod in horizontal position, this diameter is the characteristic length. So the heat transfer coefficient, characteristic length will affect on the heat transfer coefficient. Come to the description of these operators. The copper tube is inserted into a closed vessel, closed container, and one heater is provided to the tube to give the heat input to the rod, and 4 thermocouples are mounted on the surface of the rod to monitor the temperature values at various positions. And this one is the console, and this one is the heater, and this one is the dimmer stat. By using this dimmer stat to control the input power to the tube, and this one is the temperature indicator and the channel selector. By using this to monitor the temperature values at various positions of the surface of the tube. And by using this, the purpose of the console is to give the to distribute the power throughout the panel. So let us go for the experimental procedure. I am giving the power supply to the equipment, switch on the mains, and console switch on and heater switch on. By using this dimmer stat, adjust the power input to the tube, copper metal tube, and by using this temperature indicator and the channel selector, monitor the temperature readings. Here T1 indicates the T1, T2, T3, T4 indicates that surface temperatures of the copper metal tube, and T5 indicates that ambient temperature, that means that ambient temperature is surrounded by the tube. Observe here the temperature values are varying with time. So the system is in unsteady state condition. Wait for some time, the temperature stabilizes with time, that means steady state condition. After reaching the steady state condition, tabulate the values here and go for the experimental calculations. Here after reaching the steady state condition, please tabulate the values here. The power input T1, T2, T3, T4 and T5. After tabulating the values, conduct the experiment in keeping the rod in horizontal position. Main precaution is there at the time of starting the experiment, that is, the experiment should carried out in the absence of wind flow through windows, as well as the absence of fan. That is the one main precaution you should take at the time of starting the experiment. Second precaution is there at the time of keeping the rod in horizontal position. For better results, experiment should conduct after the tube is cooled down, that means almost the room temperature. Another precaution is there for comparison of results, for the comparison of heat transfer coefficient, keeping the rod in horizontal and vertical positions, the temperature should be considered for equal interval of time in both the cases. Before starting the experiment, keeping the rod in horizontal position, turn off the heater switch and monitor the temperature values of surface of the rod. So, the surface of the rod come close to the room temperature, that means almost the room temperature. So, let us keep the rod in horizontal position and conduct the experiment. The surface of the rod temperature almost reaches to the room temperature. So, let us start the experiment keeping the rod in horizontal position. Again, I am giving the power input to the rod. Initially, how much amount of the power I given to the rod at the time of vertical position, same amount of the power I am giving here. Same amount of the power I am giving here, and wait for some time. The temperature stabilizes with time. So, after reaching the steady state condition, tabulate the values here. After taking the readings, let us go for the calculation part. Before going to the calculation part, turn off the dimmer stat and turn off the heater controller and switch off the console. Okay, let us go for the calculation part. These are the values obtained during the time of experimentation. At the time of keeping the rod in horizontal position, the values are recorded every 10 minutes, and observe the last two readings here. The variation is very low compared to previous 10 minutes and after the 10 minutes. So, we considered that these are the steady state values, and going to calculate the heat transfer coefficient value for these values. According to Newton's law of cooling, Q equal to H A delta T. Here Q means whatever the heat input given to the system, and H is the heat transfer coefficient. We need to calculate that heat transfer coefficient and substitute the surface area here, because heat is transferring along the direction of surface only. Here heat is not transferring across the cross sectional area. And temperature difference means surface temperature and ambient temperature here. So, H is equal to Q by AS into surface temperature minus ambient temperature. Here Q value directly came from the table, and find out the surface area and temperature difference here. Surface area equal to pi dl. Pi into diameter of the rod is 32 mm. Convert this into meters, 0.032 meters, and length of the rod is 450 mm. Convert this into meters, 0.45 meters, and calculate this value by using the calculator. .045 meter square, and calculate the surface temperature. Surface temperature is the average of surface 4 thermocouples mounted on the surface, T1 plus, T2 plus, T3 plus, T4 divided by 4. So, that equal to 93.4 plus 109.9 plus 85.3 plus 98.6 divided by 4. .8 is the surface temperature. Ambient temperature value directly came from the table. So, substitute the surface temperature, ambient temperature and surface area in this equation. We will get the heat transfer coefficient. Heat transfer coefficient H equal to 50 divided by 0.045 into 96.8 minus 25.9. Calculate the heat transfer coefficient. (15.67 watt per meter square degree centigrade). This is the heat transfer coefficient value obtained keeping the rod in horizontal position in practically. So, calculate the heat transfer coefficient value theoretically also by using the hand data book. From the hand data book, the theoretical value is like this: HLC by K equal to 0.53 into GR dot PR. Here GR means Groshop's number, PR means Prandtl number. This Prandtl number value is directly came from the table, that is the property values table at film temperature. And GR, we need to find out the GR value, Groshop's number value, and substitute the equation. GR equal to G beta Ts minus Ta into Lc cube divided by V square. Here G means acceleration due to gravity 9.81 meter per second square, and beta means inverse of film temperature, and Lc means characteristic length. Keeping the rod in horizontal position, the characteristic length Lc equal to diameter equal to 0.032 meters, and kinematic viscosity value is obtained from the properties table. So, substitute all these values and we will get the Groshop's number. The temperatures, surface temperature is 96.8 minus 25.8 into Lc cube 0.032 cube divided by V square, kinematic viscosity 20.02 into 10 to the power of minus 6 whole square. Okay. Calculate this value by using the calculator. 168.13 into 10 to the power of 3. There is no units for the Groshop's number, and substitute this Groshop's number, Prandtl number, and thermal conductivity in this equation. We will get the heat transfer coefficient H value. H equal to 0.53 into 168.13 into 10 to the power of 3. Prandtl number 0.69 whole power 0.25 into thermal conductivity 29.66 into 10 to the power of minus 3 divided by characteristic length Lc, that is 0.032, that equal to 9.08 watt per meter square degree centigrade. This is the natural convective heat transfer coefficient value theoretically. And let us go for the calculation part of keeping the rod in vertical position and compare the two values here. These are the values recorded at the time of experimentation. The values are recorded at each interval of 10 minutes only, and observe the last two readings here. The last two readings, the temperature values variation is very low, so that's why we considered that this is the steady state condition, and going to calculate the heat transfer coefficient values for this temperature values. According to Newton's law of cooling, we know that Q equal to H A delta T. Here Q means whatever the heat input given to the system, and H is heat transfer coefficient. We need to calculate this one. A means surface area, because here heat is transferring along the surface. Here heat is not transferring across the cross section area. That's why here we are substituting the surface area. Temperature difference means surface temperature minus ambient temperature. This is the temperature value, and heat transfer coefficient surface area. So finally H is equal to Q by AS into surface temperature minus ambient temperature. In this formula, Q value directly came from the table, and surface area, we need to calculate the surface area, and we need to calculate the surface temperature. For that one, surface area equal to pi dl pi into diameter of the tube 0.32 meters, 0.032 meters, and length of the tube is 450 mm. Convert this into meters, 0.45 meters, and calculate by using the calculator. 0.045 meter square surface area, and calculate the surface temperature value, and consider the 4 temperature readings, because 4 thermocouples are mounted on the tube surface. So consider average temperature as the surface temperature of the tube. T1 plus, T2 plus, T3 plus, T4 by 4, that equal to T1 is 94.8 plus 109.8 plus 90.2 plus 96.9 divided by 4. Calculate this one. (97.92) degree centigrade. This one is the surface temperature. Already we know the ambient temperature value directly from the table. So substitute all these values in this equation, we will get the heat transfer coefficient. H equal to 50 divided by 0.045 into temperature difference 97.92 minus 25.4, that equal to 15.32 watt per meter square degree centigrade is the heat transfer coefficient value obtained practically. Calculate the theoretical heat transfer coefficient also by using the hand. Let us go for the theoretical calculation. According to our heat transfer hand data book, the formula is like this: HLC by K equal to 0.53 into Gr dot Pr power 0.25. Here H means we need to calculate the heat transfer coefficient, and LC is the characteristic length, and K is the thermal conductivity of the rod, and Gr is the Grashopp's number, Pr is the Prandtl number. These thermal conductivity, Grashopp's number and Prandtl number find out, values find out from the data book at film temperature. Film temperature means average temperature of surface temperature and ambient temperature. This one is the film temperature value, and these are the property values taken from the data book at film temperature. First of all, find out the Grashopp's number. Grashopp's number Gr equal to G beta temperature difference into LC cube divided by V square. Here V is the kinematic viscosity, this one is the kinematic viscosity, and LC is the LC equal to L for vertical position and G is the acceleration due to gravity. We know that value 9.81 meters per second square, and beta is inverse of film temperature, so that equal to 1 by 61.66. so 0.016 per degree centigrade. Substitute the values of beta, G, LC in this equation. Grashopp's number Gr equal to 9.81 into 0.016 into temperature difference 97.92 minus 25.4 into LC cube is the length of the tube. The length of the tube is 0.45 meters divided by kinematic viscosity. This is the kinematic viscosity. Substitute this one. Square. Calculate these values by using the calculator. $471.56 is the Grashopp's number value, and Prandtl number value directly came from the data book. Substitute this Grashopp's number, Prandtl number and thermal conductivity in this equation. We will get the heat transfer coefficient value. I am writing this here. H into LC 0.45 divided by thermal conductivity 29.66 into 10 to the power of minus 3 equal to 0.53 into Grashopp's number 471.56 into 10 to the power of 6 into Prandtl number 0.694 whole power 0.25. Calculate the heat transfer coefficient value by using the calculator. H equal to 5.3 watt per meter square degree centigrade. This is the heat transfer coefficient, that means natural heat. This is the natural heat transfer coefficient value obtained theoretically.